Is that better? Okay, good. So 2 parts. Let's get going with the first one, Bitter Lesson 2.0. In a workshop on generative AI, I guess the elephant in the room are the latest and greatest models that we have today. Great video models like View 3. And if you haven't seen it, this is kind of what you
A detonation has just occurred on the outer ring of the city. We'll now be going live to our top influencer opinions.
OMG, people, the world is ending. Are you seeing this? This is actually so exciting.
Friends, this is the breakthrough moment from chapter 7. When everything falls apart, we rebuild ourselves stronger.
Everything is fake, including me. I'm a construct created by the Door brothers. Anyway, here's Tom with the weather.
Every day felt heavy. I felt trapped.
Then I tried Puppermin.
Our prescription helps your body secrete a special pheromone that attracts puppies.
I took the pill before bed, and when I woke up, there he was, the love of my life.
The pill does not target depression directly, but we've found that it's really difficult to be depressed when cute dogs show up at your doorstep.
I used to feel so empty, but now I feel joy and mild concern how a pee stain got on the ceiling.
All right, I like this, how we are close to the end of the world and then we're just turning back to the weather. Now we've seen a lot of generative models come and go, some which we cherish, some which not so much. And the question is really, what's out there? Do we have, with what I've just shown you already, kind of the final model there, which we just need to scale up to solve all our problems? Or is there more needed? I guess that's the other elephant in the room. The driving force behind pretty much a lot of things that we've been seeing is scaling up these models at a significant rate here, like 4x, like we got like 15,000-fold increase in model size over some 5 years. And pit that against the growth of the compute hardware that we have, which is like, what's that, like 1.3x per year. And if you put both side to side, it's clear that we're set up for trouble. I coined this year delusion of scaling. I'm not going to say with that scaling doesn't help. It for sure helps. And we've seen a lot of the positive outcomes of scaling models. But if you outrun with your model size the compute, you're set up for trouble. And frontier models have been significantly growing in not just model size, but also in the cost of their training. It's judged almost like 2.5x per year. And the question is really, what's our solution to that? Our solution to that so far has been to just throw more money at that. My understanding is that money does not exponentially simply go up. And with that, projections target like $1 billion for training in just a few years to come. But what's clear is that training data will also be tricky to scale, at least uncorrelated training data at that scale, let alone like what we do with content producers, meaning like things get more costly there as well. And if you then look at just recent interesting events on a bond market where things are starting to flip over, well, we'll see what trouble is going to happen. But what's clear is that we cannot scale up money as we've been doing so far to buy ourselves time, essentially. So in short, I guess we've been pursuing this game by building ever bigger ships. And that's what Rich Sutton targeted in his Bitter Lesson, where he said that the breakthrough progress that we've seen eventually arrives simply by scaling up computation. Now, with that, I think we are where we've been in the transatlantic shipping business 100 years ago, which was all about building bigger and faster ships. And this was not superseded, or this entire business was not canceled by an iceberg, not by the World War, but it was ended by that, the jet engine. Yeah, and that means that simply scaling things up were in the past not the solution. And I think with that, it's probably also not going to be in the future the solution to all our problems. And that brings me to what I coined the Bitter Lesson 2.0. The Bitter Lesson Sutton's bitter lesson actually assumes that critical commodities such as compute are scalable and that they're cheap to scale. And if that holds true, then everything that he implied from that is also true. But we've just seen on the previous slides that that's not fully true. Compute past Dennett scaling, which ended in 2007, does not simply scale as fast, even for GPU computing, as it did in the past so far. And that meant that models get more expensive. Model training gets more expensive. So what's the way out? It means that simply this, at the bottom, you see here, this exponential curve does not continue that way all along. If things get more costly, there will be some flattening out. But in the past, we used paradigm shifts to get ourselves out of this pit. It was the jet engine. The GPUs that you're using today aren't electron tubes on steroids, right? We had transistors coming about, integrated circuits, and so on. Paradigm shifts that got us to where we are and reset essentially this sigmoid curve and got us to a new start. And with that, I think it's time to reconsider another wise guy, Vapnik, who back then said that when you're targeting a problem of interest, you should bear attention that in so doing, you're not trying to solve a more complicated problem than your ultimate problem that you're targeting. He said more general, I guess for the purpose of what we're discussing here, it actually means a more complex problem. And with that, the question is really, where do generative models, where do foundation models stand here? And to that I added, well, you shouldn't target a more complicated intermediate problem unless the bitter lesson above applies, meaning that for this intermediate problem, you actually have better scalable commodities, better scalable data, and whatever that is. In that case, what Vapnik said does not apply, and examples of that are pre-training, for instance. When you have a medical problem that you're targeting, for instance, and you have only scarce data in that modality, then pre-training is very helpful. Foundation models can be very helpful because there you have much easier to scale data. Another part, which I targeted in other keynotes, is 3D as opposed to video. We all know that 3D data is significantly trickier to obtain than video data. In that case, I think it does not apply, and we're probably then closer to what Vapnik has been saying. And lastly, the question is, will we obtain true intelligence merely by scaling? There's evidence for that, like work on emergence in large language models. But I think we've also seen plenty of evidence against that. Machine learning approaches typically take an empirical approach to building models, and it's still a far way over to really building physical-based models that you can then actually utilize, interpret, and the like. Long story short, and that's the second part here to this bitter lesson 2.0. If we want to really attain true intelligence, in nature so far, it's been always learning and acting based on finite resources. Last time I checked, our brains haven't grown for the last 200,000 years plus. And nevertheless, we've moved from an age, Stone Age, where we're just dealing with sticks and stones, to operating complicated machines. And it turns out the same paradigm we've also been happily using in AI, right? Bottlenecks in our architectures, which force abstraction, and with that target generalization. Take latent diffusion models, because you mentioned it, and other approaches like the autoencoder that you see here. All approaches where scarce, finite resources focused us and forced us to actually develop more intelligent approaches. And that begs the question, like, will we just be scaling models up? Or if you're not having infinite resources, and even apparently the big tech companies, for the complexity of the problems that we're targeting, have finite resources, efficiency will become a problem. And if you want to scale up these models so that the millions and billions out there can use it, even then it's becoming a more pressing issue. And second off, how can we get more control in these models? Because, I mean, of course, there's been less cherry picking than there's been before, but me talking to directors, me talking to actors, they don't like you just presenting them some nice output. They have a picture, they have a movie in their head, which they want the machine to help them produce. And if you're just a bit off, they don't like that, right? They want their idea, which they have in their head, to be spelled out. So how can we give them the control that they can do that? So in this part of the talk, I will be discussing a bit how we can recycle generative models that have already been trained, and with that cost quite a bit of money and time, how we can recycle them to eventually boost the efficiency of this entire process of model building, how we can add control there, and how we can repurpose them for entirely different modalities. Now, the thing that comes to mind when I'm talking about repurposing models and adding control there are probably adapter approaches, right? We take your favorite generative model and you're adding control to this model by adding an adapter where you can fix certain properties. Let's say you want to fix the body posture that you're having here, and you then have your text prompt, high quality, detailed, and professional image, and you get just that out. Now, by fixing certain parts, like the shape here, I can alter the text prompt, as we all know, and get different images out with certain aspects focused and fixed. These adapter problems, however, come with a problem to them. If I give you different ways, or if you have different ways to adjust your scene in mind, there's not one adapter to rule them all. You see here an invisible divide. At the bottom are approaches that control the pixel level, fine-grained structure of this scene, fine-grained details of this scene. At the top are approaches which control more like the overall style of the image that you have. And it turns out that there is no single adapter to rule all of these problems, but that you need to choose the adapter, train a particular adapter for the respective problem that you're actually looking at. Now, we've been working, and this is last ECCV submission here, ECCV paper, on an approach which is efficient, flexible, and which generalizes across different models, different AIs, so not just like Stable Diffusion. You can slap it on top of whatever you want, but most importantly, you can utilize it to control the local fine-grained structure, vertical axis here, and the overall context of the scene on the horizontal axis. You see us here top right, size of that circle tells you that the approach also has significantly fewer parameters, and with that, it is more effective to train this approach. Now, how do we get this going? What we envision is actually taking adapter approaches, which, as you know, establish a bypass to your generative model, encoder-decoder architecture here, which you need to train on your very conditioning signal that you have, for instance, a depth map in that particular case. You need to train that, and if I give you some other conditioning signal, you need to readjust them. Our goal was to make this a zero-shot approach, which you train once, and then you can change the conditioning signal and utilize the approach again. And for that, we observe that if we have a low-rank adaptation, and we go to this low-rank space, we have a few parameters only compared to our input modality, a very compact representation. And if we in that space add an affine deformation there, we can easily sort of transfer this representation over, essentially make this a conditional adapter, which you can on the fly adjust. On the fly meaning, in the bottom right corner, you see different ways of conditioning the approach. We proposed here to have two neural networks, one which controls more like the overall contextual properties, the other controlling more like the local details. And these then learn to take arbitrary content on the input side and in a zero-shot manner, by means of this low-rank adaptation, adjust the adapter to whatever input you have. Now with that, you can take an input signal, which can be just the overall structure, which can be the context of the scene, and you can then adjust both of them individually to create whatever fabrications you want, or this novel animal there, which I haven't seen so far, and essentially control the in-betweens. But not only that, this approach now works for arbitrary input control signals, be it overall style of the scene, a depth of the image to give you a bit of 3D structure, an edge map like HUD, or human postures and the like. And now with that, you have an adapter which you can on the fly take to adjust your generative model to whatever control signal you want. Now, let me switch gears. We've trained these generative models, and a lot of those are actually being used to simply generate images. But in generating images, we've essentially been learning a representation of our world. And with that, a lot of people have asked themselves, can't we utilize this representation also for something else? And yes, DIFT features and the like have been used for just that, as a representation of the local signal in an image. This is going to be an oral at the CVPR in the first session, which is on Friday morning, where we want to improve on these very diffusion features. And improve, I'm going to show you now in what aspects. Now, if you take these diffusion features as a local representation, you of course can utilize them to establish, for instance, semantic correspondences and solve a lot of other tasks on top of that. We've, as a community, been working on a lot of different features, right? Started off in the humble old days, handcrafting these features. Then there was a lot of supervised learning, which boosted the features more and more in an end-to-end manner. And quite recently, we've seen a lot of self-supervised strategies to actually learn feature representations. Out of these, the emergent features that you get out of generative models, I find fairly striking. If you look at, and this is the reason why I find them striking, if you look at the taxonomy of correspondence problems that you can tackle, on the far left, you see fairly easy geometric correspondence problems, where you essentially establish correspondences across viewpoints. We then see here problems where you go across classes, across articulation, until you finally go really across different levels of taxonomy. And here, generative features like diffusion features really stick out. Yeah, you see here SD 1.5, very old model, base DIFT features giving you already an edge over the Dino feature, but in particular, they are complementary to the Dino features, and combining the two gives you really an entirely sort of different league of features. But still, if I look at the diffusion features and apply them here in a video, you really see a lot of noise happening. On the left-hand side, you see that the correspondences across these different images, as long as they're somewhat close, it's still working out fine. But then for the dog at the bottom, the match is really off. What are the problems? Problem one, if you have a diffusion model and you take its features, there's noise involved, right? And adding the noise actually reduces the signal, of course, of our features. So if I take the feature out of this process, the more noise, the more tricky it is. And the optimal feature is not achieved at zero noise. Secondly, the optimal time step varies. Depending on what you want to do with your feature, you will observe that you need to take different time steps, and you need to really adjust this time step depending on the particular problem that you actually want to solve. That brings us to the solution that I want to propose here. Let's look at the diffusion features. You take your image, you add noise, you get a noisy image, you run it through the diffusion process, then you grab some internal layer there to give you the noisy features. They're useful, but noisy, and you're not having a single feature, you have different ones depending on the noise level that you're going for. The naive solution would be, well, you just remove the noise there, run that through your model, but that's not going to give you any useful features, because we need this noise as we've seen beforehand, and you're not getting the best features for zero noise. That we've already covered. And here's an observation. This diffusion process here gives us noisy features, but this noise process is actually an additive process. You get the features at x0, but you get the features, the noise there as a roughly, approximately additive component added to the noise-free features. And that motivated us adding the second copy here of our network and a loss function. The second network, however, as you can see, does not take the noisy image as input, but it takes the clean image as input. And then we want to minimize the loss here. And the second network evidently has the ability to take all the information from the clean image in and make sure that the features are somewhat comparable in their semantic abilities to what you got from the DIFT features in the first place. Still, in that case, you're not getting a single feature, right? You're still having this parameter of time here to your left. So how can we still handle that? For that, we added a projection layer which now takes in the time conditioning signal. And you then go across all different kinds of time steps and make sure that this loss is getting minimized. So you essentially shuffle all of this time optimization into this projection layer, which then gives you a feature here at the bottom, which is a clean feature because it's seen the original image, and it can optimize over all the particular time steps. Results? Well, you get on the left-hand side DIFT features, which are fairly noisy and flicker from frame to frame. On the right-hand side, our clean DIFT features, which have been optimized by simply half an hour fine-tuning on a single A100, and then fairly consistent across time. If you do correspondences on the left-hand side with DIFT, you're okay as long as you're semantically close. But if you're further away like this dog, things fail. With the CleanDIFT features, you get the correct correspondence in this particular case. And last off, these features work on different types of methods. Like on the left-hand side, you see in orange our features being added on top of a DIFT approach, but also other approaches, other base architectures essentially, and giving you a gain on top of them. Right-hand side, you see PCK here over different backbones applied, SD15, but also other backbones, and you see the gain that we're obtaining there. Now, if you want to know more, please talk to us at poster session or after the oral session, first session on Friday morning. And with that, I'd like to switch gears. Generative models have been used not just in the image domain, not just to give you powerful features, but evidently also in the field of 3D. And after a lot of nerves, we've recently seen Gaussian splatting becoming really a very powerful alternative. Now, what I'm going to propose here is an approach which gives you Gaussian splats in a significantly faster manner and also at a significantly higher quality than what you were getting with standard 3D GS approaches. Now for that, let's look at how 3D Gaussian splatting typically works and identify some issues and see how we can actually address those. And this is going to be a very simple strategy to actually tackle the issues, embarrassingly simple strategy. So usually when you have 3D Gaussian splatting, you initialize it. You initialize it with a structure from motion approach, which you're seeing here, which gives you initial Gaussians. On top of that, you add a projection. You do your splatting through a differential renderer, which gives you the final representation there on screen. That you compare against your ground truth image. You see where you did mistakes, backprop through your differential approach there, your rendering, and see how you need to adjust your 3D Gaussians, their parameters. You do that quite a bit of time, and then you realize there's no way that you can go further. What you're lacking are more Gaussian splats. And in that case, you densify your Gaussian splatting, add more Gaussians to the game, and then your optimization continues. But there's an issue with this process. You've been optimizing for a while. where you simply did not have any chance to get any better. This iterative densification process there risks a certain amount of inefficiency. You have Gaussians, which you apply to the scene, and then you realize they're not going to go any further if you optimize them. We somehow need to add more Gaussians to the game, or pruning strategies, which you see are also being in place. But if you look at the high frequency details of the scene, you typically figure out you need many, many more Gaussians, and typically your initialization and all the optimization that you did based on that only went so far. Why? Why? Well, if you look at the local high frequency details here of your scene, you get a lot of individual pixels, which are all different. The initialization coming from structure from motion places a single Gaussian there. Well, it's all somewhat greenish, right? But a lot of pixels are drawing in different directions on the parameters of this Gaussian. Now, question is, what is this Gaussian going to do? Well, this optimization can only go so far, right? Until you add significantly more Gaussians, and then finally you have the number of parameters that the optimization can really kick in. But beforehand, 3DGS is essentially waiting for the right initialization. That's why we propose the edge approach, which you're seeing here on the right-hand side, where we try to initialize the Gaussians much closer to their final sort of coordinates and denser. So dense that we don't require any further densification later on, that you essentially have all the parameters that you require towards the end and optimize them then to their perfect coordinates. How does this spot-on initialization work? Well, we eliminate the need for densification by utilizing state-of-the-art dense matching and triangulation approaches, such as ROMA. We played out with a few others, which you're seeing here at the bottom as well. And we get somewhat comparable approaches, as long as you're not going for flow-based techniques, which are definitely not built for what we're having here in mind, like Raft. But everything else, in particular ROMA, gives you fairly dense correspondences that we can rely on to give us 3D localization of our Gaussians, their correct size, and utilize these points in the camera rays to initialize the Gaussians to a location which will already be very close to their final spot. And the color we can then get by essentially averaging the points under a Gaussian. With that, and the Gaussians being close to their final location already in the initialization, the Gaussians need not move very far, and we get the same quality or better quality significantly faster. Not move very far, you see this here. Horizontal axis is how much the Gaussian needs to travel. In orange, our approach, and you see that this is significantly fewer optimization steps, significantly fewer traveling that we actually need. And with that, our initialization bottom right here is significantly better than what you get out of standard structure from motion. And if you compare the speed, which we have, x-axis, the quality, which is on the vertical axis here, you see that the approach compares favorably with other 3D Gaussian splatting approaches so far, both being competitive against those approaches which want to maximize out on time, as well as on those approaches which want to maximize out on performance. And you can see in the video here how we, after our initialization, already get something which is really sort of good in terms of quality and the overall time, although the optimization took significantly less than for the standard 3D GS approaches, gives us better quality. We have demo on Hugging Face. I encourage you to just go there, check out with your own data, and play out with that and see how your results actually look like. Here's again an example, half the optimization time and significantly better performance in what we achieve. So let me wrap up this part. We removed the need for any iterative densification by means of having a direct triangulation of the densely initialized 2D key points and map them then directly to the 3D Gaussian splats. We've seen that the Gaussians are with that much closer to where they eventually need to go, don't need to travel that far, and we get better convergence and better reconstruction fidelity. And with that, our approach outperforms speed and on the other end also quality optimized 3D GS baselines significantly fewer optimization steps required here, 6 times fewer, and 40% less Gaussians required. It's plug and play compatible with existing acceleration methods. You can just slap it on top and get an extra gain here. And then the last bit, and then I'm done, is going back to the training. I've so far shown you what you can do if you have these approaches, how you can repurpose them, how you can actually optimize their efficiency. And the last bit that I want to show is what you can actually do if you want to speed up the efficiency of your training process. Now, many approaches these days, and the majority are probably in one sense or another transformer-based, because it's one architecture which really nicely scales with data being there available, large amounts of data being available. But it's clear that transformers also have a complexity issue, right? Because they establish by means of attention powerful contextual relationships across scenes that, however, becomes costly. And with all the optimization to transformers that has been done, at the end of the day, pruning strategies rule, where you simply, you see this at the bottom, take individual tokens, you throw them in the trash bin, and with that, with fewer tokens in, quadratic complexity doesn't hurt you that much. Or masking strategies, where you take a token, throw in a trash bin, but then late in the process, you reintroduce an empty token, so to speak, so that you can do at least a tiny bit of processing with this token, and you've not eliminated this breadth of your model there in all its entirety. But still, it violates assumptions of our diffusion process there. Our diffusion process requiring that in each processing step, we do only tiny updates to the scene. In that case, you take the noisy signal, you replace it in a very late layer, with essentially an empty token, and then the model has, in very few processing steps, take this empty token and ramp this all the way up to the final signal. That violates our underlying diffusion assumption. And that's why we propose here routing strategies. Token routing strategies, which take the noisy token and rather than eliminating it, essentially bypass part of the computation, but now not introduce an empty token later in the game, but essentially introduce the noisy token. I hope that you can now see that now we are closer to the final assumption again of the diffusion process, that we take something noisy and we do tinier steps to actually denoise that than if we simply start with the empty token late in the game and have to deal with that. And that actually improves here significantly on training. Improves on training? Well, let's see. If you have on the vertical axis performance plotted as FID, on the x-axis the training time, you see that you get the same performance at significantly reduced, significantly more than order of magnitude, smaller computational budget. And I guess that's good news for everybody in the room who does not have infinite compute available. That's a way to actually get the same or even better performance at reduced computational budget. Now, it's important to say that you can combine our trend approach with other approaches like DIT approaches here with and without conditioning and get significant gains there. And you can combine this approach also with other strategies like RIPA, we did it here, and different base architectures that we investigated on, and always get a gain. So you can nicely plug and play, combine that with other approaches as well. And now in the interest of time, I'm going to wrap up. First part, I think it's time to really embrace this bitter lesson 2.0, as I called it here, and figure out where we stand in the respective problems that we're looking at, whether we are more like Babnik, more on the Sutton side, depending on the commodities that we actually have available for our particular problem. We know that this may be different, the slider may be different, whether we're, for instance, in 3D or in the video domain, whether we're looking at images, language, and so on. And with that, we come closer to answering this ultimate question, how we can attain something which is closer at least to true intelligence, and answering this question whether for particular domains we can achieve intelligence by mere scaling. But whatever it's worth, and I guess at a conference like this, it's important to bear in mind that these paradigm shifts are the critical part, right? If you're a company and you need to invest your money right now in improving performance. Of course, you're going for the scaling game, right? But with thousands upon thousands of people here all investing exactly on the same card and just scaling your models up, let's use the pluralism that we have. In the past, we were really great because one or a few of you will then figure out the next paradigm shift, which gets the wheels turning. Next up, we've seen approaches how we can very effectively take already trained models and adjust them in a zero-shot manner. Really have an adapter which is conditional, which you don't need to retrain. You train it once and you slap different inputs in and you get the conditioning that you want. In an efficient and a flexible and a model agnostic way, get this zero-shot control. We've seen how we can utilize generative approaches to give you features. But that so far, this typically meant that you have 3 parameters to adjusting your features, that you require adding noise to your features to really get the diffusion process kicking in. And with the CleanDIFT approach, we've seen an example how you can actually avoid this and get the true rich signal out of your image. We've seen how you can, by means of a very simplistic strategy here, improve on 3D Gaussian splatting by a significantly better initialization of the Gaussian splats, get closer to your initialization and avoid this iterative refinement process. And last off, if you need to train and you have these very powerful transformer-based architectures, how you can avoid pruning and masking strategies, which turn out to be suboptimal, and replace them rather by routing strategies, this thread token routing strategy. With that, let me thank you for your attention. I'm happy to answer any questions if you have.